Hello, and welcome to another edition of DDI's Productivity Webcast Series. I'll be your host, Joseph Richter, and today we're going to discuss another one of my favorite topics, design planning. Design planning is basically a logical approach to modeling. As we make parts, we quickly realize that these parts wind up changing. In other words, they don't stay exactly the way that we initially drew them out. Therefore, to make our lives easier with design planning, if we can plan out for changes, even though you don't have a crystal ball, you can typically determine how a part's going to change, and we'll walk through here and show you how that's done and how we can do that inside our models. So the topics that we'll cover today will be stages in the design planning process, in other words, how to get started. We'll talk about design intent. Design intent is key to leveraging the power of a 3D parametric solid modeler like SOLIDWORKS. Design intent is basically the topic that allows us to take our intelligence and plug it into our model. The rules that we intend for it to follow, therefore accommodating changes. This is so important that those of you that have heard of the Certified SOLIDWORKS Professional Exam, this is basically what that exam is all about, whether or not you have a grasp on design intent. We'll discuss that more later. The third topic here will be tools that will enable us to capture our design intent. Then I'll describe some best practices to follow. And then to finish out the presentation, we'll discuss some final thoughts on the subject. The first topic here is going to be stages in the design planning process, how we get started. The first stage is to identify the specifications for our part. First thing we want to take a look at is obviously fit, form, and function. Fit is how this part is going to interact with other parts, or maybe if you're buying a part or getting a part from somewhere else off the shelf, the interface would be critical to our part since it mates up with it. Other considerations here would be clearance with other parts, or maybe from a real-world standpoint, can this part be installed easily, or if it's a high-wear part, can I replace it or maintain it easily? This kind of ties in with clearance with other parts. If we're working in tight quarters, will my part wind up occupying the space that was set aside for another part? The second one here is form. In other words, what's the configuration of my part? Does this part have symmetry? Or maybe how this part looks, aesthetic-wise. This would be important to consumer product designers. An important consideration for form is whether or not this part is even manufacturable. Perhaps the cost. Can we get the cost down? Can we make the part simpler? Okay, so that all ties into form. And finally, function. How is this part going to work in the final assembly? What is the purpose of this part? Why are we designing it? Or maybe another consideration, if this part is going to retrofit or replace other parts, can it do that? And if it's going to be doing that, can we replace more than just one part? The second stage here is to sketch out a basic layout of our part on paper and pencil. This will allow us to plan out the following: our datum structure. This will be used in the final drawing, or if your company has adapted ASME 14.41, that is the standard by which we can utilize a 3D model in place of a drawing, so long as that 3D model contains all the information that would otherwise be present on your drawing. Another thing that we can plan out on paper would be the placement of our planes for use in sketching. If you have a complicated part, depending on how you model it, you might need a lot more planes than if you had taken a few minutes to plan it out up front. Another good use of the placement of planes, would be symmetry. If we're going to mirror our part, we would need a plane through the middle of our part, if that's what we're trying to mirror about. And finally, for an assembly, if you have a complicated part or an ergonomic part especially, and you don't have very many planar faces on it, when you go to mate it up in the assembly, if you take a sphere for example, there's not a whole lot of mates that we can apply to that other than tangency and concentric. However, if our planes are in the right spot, we can utilize those planes to create distance offsets, coincident or parallel, what have you. The other consideration here would be the features to be used, specifically the order of the features, because the order of the features determines the outcome of that model. And finally, the approximate number of features. If you have too many features, it might take the computer a while to rebuild it. However, if you have too few features rather, then it's going to limit your flexibility and make changes awkward. One of the things that I like to talk about here for number of features is you want to utilize the number of features to accommodate all the changes that you expect to see, but yet you don't want to go overboard utilizing 5 features for an 1/8 inch fillet when all of those fillets could have been done in one feature. So, you want to use the number of features that are necessary. Next, we want to identify how we expect this part to change during its design life cycle. In other words, if we know a shaft is going to get longer, we want to make the model so that way the shaft will get longer. If we know that a bearing is going to move around in the shoulder on the shaft, we know it's going to move closer to one end or further from another. We want to make sure that our model is designed that way. In other words, it's dimensioned from the end that we're trying to control it from. And finally, from this whole layout, this will help us determine our design intent. And with that, I'll take you over into SOLIDWORKS, and I'll show some examples of this. So here inside SOLIDWORKS, I have a plane here, or I have a block with 3 different planes here. And here we're going to talk about placement of planes. And as I take a look inside this sketch here, we can see that this particular model was started sketching at the origin. Now, the one key thing to keep in mind about origin is what's actually happening at origin. In geometry, a point is the intersection of 3 planes. And as we look here, we can see that the front, the top, and the right all intersect right at our origin. So in this scenario here, my model faces of this rectangular block, these faces all share the same as the plane itself. Now, why that might be important is if you needed more places to sketch on, I'm not gaining anything based on my origin location. Like I said, this face is the same as this plane here. This face over here is the same as this plane here. As I'm moving this around, you can see there are some annotations on here, things like datums, and I even got dimensions with tolerances. Okay, as I made mention about ANSI 14.41, this enables us to take advantage of our 3D model as a drawing, so that's what this is all just thrown on here for. As we take a look at our next example, maybe a better way to start this part, as I take a look at one of my sketches here, you'll notice if you've watched any of our demos or some of our other webcasts that we typically wind up drawing a rectangle with a center line going from corner to corner, and usually utilizing a midpoint relationship with that center line and the origin. Okay, what this does for us is it centers this rectangle on that origin. Through trigonometry, we know that 2 right triangles with equal sides are going to have the same length hypotenuse. Basically, that allows us to have a mirror, and if I delete these here, we'll go ahead and take a look at what I'm talking about. It's mirrored about both axes through that angular line. So, I'm going to go ahead and cancel out of this, discard my changes. The next thing that I want to show you for placement planes is this one here. This model might be fairly difficult without accomplishing or making different planes. But if you take a look at my tree here, I don't have any additional planes. If you look where my origin is, okay, I chose my origin in this location because I knew as I went to model this thing that the first profile here is going to be fairly complicated, but with all these planes in the middle, as I show the next feature, build one on top of another. Here's a circle. The one going down was a rectangle. As we take a look at that one here, because all those planes are right there in the middle, I'm able to use the top, front, and right for all of my sketch geometry. Extruded 4, that was simply done on the front plane. And in each one of these we're doing a mid-plane extrusion. Mid-plane basically takes our total depth and splits it about that plane through the middle. Okay, so this is a good example of planning out where that origin is going to be. Will vastly improve how easy it is to make a fairly complicated model. And the next example from here is going to be in an assembly. As I made mention before, a couple of spheres. These here might be nearly impossible to mate together if I didn't have their planes. So in this scenario here, I'm taking the two front planes in each one of these spheres and specifying a distance between them, 150. Okay, now I have the ability to have these spheres fully defined, located 150 from one another. Okay, next here we're going to talk about more design intent, or rather what design intent is. Design intent is the plan of how we want this model to react to changes. The key theme here for this webcast is planning. Okay, so some examples of design intent in a sketch would be how a sketch is dimensioned, which relations are being used, and the proper use of link values and equations. As I mentioned before, SOLIDWORKS is a parametric-based modeler, and I also mentioned that we can plug our intelligence into our models so they change how we want them to. Therefore, how we sketch and dimension and take advantage of relations will all change the model depending on what we actually did. I'll go through some examples of design intent for approach. 3 types. We have the layer cake, which is like a stacked up approach. Typically want to avoid that, and I'll describe that here in a second. The potter wheel, which is basically one revolve feature. Yeah, it makes your part really quick, but it limits your flexibility. Another popular approach is the manufacturing approach, whereby we start with a block and we just start cutting away on it. We'll also show some examples of design intent in features like different end conditions. We have other end conditions besides blind. These other end conditions are typically a lot more intelligent than blind, so they will accommodate changes as the part flexes. I'll also show some examples of using link values and equations. A good example of this would be a cube. If you know that all the sides are equal, you could link all those values together as equal. Then finally, I'll show some examples of design intent in an assembly, planning for configurations, or even planning for sub-assemblies. Take a look back at SOLIDWORKS. Let me close some of these really quick. Alright, next one, sketching intent. Now, how we dimension something in a sketch is going to impact how it's going to change. In this scenario here, I am controlling the center to wall on each one of these, both on this side and on that side. So if I double click and start making a change here, 1.5, and I hit rebuild, I can see that that is basically moving to the left. If I change this, it'll move to the right. Okay. The second scenario This is going to be most desirable for the manufacturing floor because we're all coming from a datum reference edge. Have 1 inch, 3 inch here. If I change this, all these are going to come towards the left hand side. So as I modify this here, I can see that it's all tied to that edge. Now this doesn't mean that you need to make everything from baseline just because it's going to be desirable from the model. In fact, we can still say, okay, SOLIDWORKS, I want this to be centered about my part, which I did a standard mirror here. I did my dimension on the 1 and then added a reference dimension. And the reason this is all important, what I'm talking about, is when you get to the drawing, ultimately you want to be importing your model items, thereby not redimensioning the model but literally pulling in these dimensions. And this also works not with just symmetry, but if I take a look at this sketch here, I've got a different value from edge to edge. However, I still have this dimension that will wind up on the drawing. And the way that I can prevent this dimension from coming into the drawing is if I right click on that dimension, I can uncheck this marked for drawing. Therefore, when I insert model items, that item will not come into my drawing. The other thing I mentioned here was how dimensions are created will determine how they change. So as I edit this sketch here, I've got 2 rectangles. And as I dimension this one here, I'll dimension just this one edge. Okay, I'm going to click on that one edge and drop it. Or down here, I'll click on point to point and drop that. Okay, so far so good. Now on this one, I'm going to dimension edge to edge. Okay, two entities. And here I'm going to dimension edge to edge. Okay, on the surface these dimensions look identical, but here's where the difference comes in. The difference comes in when things go wrong. Okay, when things go wrong, our true intent comes through. So as I start deleting these here, I'm basically just grabbing all of them, hitting the delete key. Okay, when I start to pull on this one, how do you think it's going to change? If I start pulling on this, okay, my shape starts changing. Okay, this really doesn't look like the original square. If I pull this, I can almost turn it into an arrow. Over here, if I start pulling on this, think the same thing will happen? Well, let's take a look. If I pull on this, take a look at that. It's basically behaving like a parallelogram. See, what's actually going on in these scenarios here is this over here, it's maintaining the distance of that edge. Or here, it's maintaining the point-to-point distance. Over here, we asked for edge to edge. Likewise here, edge to edge. So that's exactly what it's doing. So this edge might be a little bit longer than that one, but this part will be easier to fix after stuff has gone wrong. Not to mention in the real world, since nothing is perfect, this is more accurate as far as what you're actually going to get out of a machine. Not everything's going to have perfect 90-degree corners anyway. To show another example of how a dimension determines how something can be changed is in this scenario here. On the top set, I'll dimension center to center on these circles. And as I change them, obviously it moves that. And now on the bottom set, I will dimension arc to arc. Okay, move so far so good, the same. Okay, here's where the difference comes in. If I take a look at this top dimension and go to properties, okay, the only thing I want to point out here is that there's nothing here. Might not mean much yet, but if I take a look at the properties here, I've got an area that was missing on the other one. Arc conditions. From here, I can specify where each arc condition is. In other words, auto recovery, I should probably turn that off. Here I can specify center to the minimum or the maximum as it flies out over here. Okay, min and max. Or min. These arc conditions are only available if you dimension edge to edge. So that's what I'm wanting to show there. Okay, the next file I want to share with you is going to be design intent examples. So as I take a look at number 7 here, this one is the layer cake or the stacked approach. As we take a look at the drawing, these dimensions were imported from the model itself. As I take a look at this model here, I can see how this part was designed, or built rather. We took a circle and extruded it up. Here we took another circle and extruded it up from this face. Same thing here. Took a circle from here and extruded it up. And finally, the last circle, took it from that edge and extruded it up. If I need to change the overall length of this shaft, I'm not really able to. I'd have to modify one of these. And as I modify one of these, that change ripples throughout the entire part. Okay, so probably not the best approach. Not to mention that this will wind up giving you a tolerance stack up, as this has a tolerance, this has a tolerance, so by the time you get out here, if everything's plus or minus 5, you're going to get 5, 10, 15, 20, okay, on your overall just because of the way you dimensioned it. And that's kind of what it looks like here on the drawing. Now I'll open the next one here. Number 8, the Potter wheel approach. I'll go ahead and show where this file is. Come on. Alright, as I take a look at this part here, you can see how it was designed, how it was built. Just a single sketch, single revolve, single feature. So as I edit that sketch, it looks like the datum structure was taken into account. I can change the overall length of this shaft. Everything looks good. However, if I need to make a change like eliminate this groove, maybe I'm trying to write an MOT through pictures and I want to show the shaft as it starts as a solid piece and then lathed down this section here and then finished out with that groove. I can't really do that with this particular model. However, as I'm talking about the manufacturing approach, that's the one that we're going to show next. In this scenario here, dimensions look the same as on the other one. And as I open this part here, I can see that this part was generated, multiple features. Okay. Simple extrusion here, circle, here's our stock, then we just cut 2 items out of it, there, simple rectangle, and then cut the groove out. So I could suppress each one of these cuts, making multiple configurations to build my MOT. You start here, you make your first cut, finish out with your groove cut. And the reason I'm saying simple is if we take a look at the Potter wheel one more time, so I open this part here, this sketch, aside from it being incorrect in the fact that I can't change it very easily, is the fact that this sketch is what I like to call a complicated sketch. In other words, if somebody else has to figure out what the heck I was doing in this sketch, it might take them a little bit longer to figure out what was going on than the other one where all I had was a bunch of rectangles. So keep that in mind as you're doing this. Now we'll talk about tools that allow us to capture our design intent. Intelligent features such as end conditions. We have more than just a blind for our extrusions. We also have the ability to do some in-context modeling. We'll talk about the whole wizard, whole series. We can take advantage of patterns and mirrors if it was planned out right. We'll discuss the proper use of sketch relations and equations. We'll talk about planning for the use of configurations and design tables. And then from a drawing standpoint, the file properties. This is part of our design planning. If we want to control certain properties, in other words, who drew this, what its description is, what its part number is, that all needs to be taken care of up front. And once we have those properties, we can plug them into our drawing as parametric notes, or we can even pull them into our bill of materials. And here we're going to go ahead and talk about end conditions. If I take a look at how this model was made, I have an extrusion. But as I take a look at this extrusion, I can see that I went up to surface, up to a plane. That means if this plane changes for whatever reason, make that 5 and rebuild. Okay, my extrusion updated. Notice I was modifying the plane. If I take a look at my next feature, I've got a couple of link values as I edit the sketch. I basically wanted an offset here. I wanted these to be equal, and to do that, when I double click on here, I had the ability to up front link values, by which I could come in here and give it a brand new name or link it to an existing group, which in this scenario was flange. And did I link the length? Not yet, but I can do that, the depth rather. So I double click on here, I can link the value to my flange. Hit OK there. So now I can go ahead and take a look at the rest of my features. And as we talked about whole series, or whole wizard rather, we're going to do whole wizard first. Whole wizard is basically an intelligent set of holes. It's linked to a database. And as I take a look at this feature here, this allows me to change what this hole is right on the fly. If I wanted this to be a tapped hole instead, I can specify the tap, 832, tapped hole. And I could even specify through wall. Okay, Whole Wizard makes for quick changes. And one last example of intelligent end conditions, as I edit the feature on this one, I can see that I did offset from a surface, this back surface here, and I said, okay, no matter what happens to this part, maintain half-inch wall thickness there. And to kind of show that, I'll go ahead and give us a cross-section view. And as I modify this plane dimension to be 5 again, when I hit rebuild, I can see that that half-inch has been maintained. I'll go ahead and cancel that and let it stay at 3.5. Okay, the next file that I want to share with you is in context. An in context part is a part that was designed in the context of an assembly. So in order to do this, I can go and insert a brand new part, and I'll go ahead and call this one a gasket. And as I place it on here, it takes me straight into editing the sketch at my new part. And I'm going to go ahead and convert that outside edge, maybe grab the inside tangent edge, convert that. Now I can go ahead and extrude this. 100th thou is good. And now I go back to editing my assembly. So now if this thing changes to 50, I hit rebuild, my gasket updates. Now I'm going to go ahead and mate this part back down here. In order to hold this cover on here, I'm going to need some holes there. So rather than going to each one of these three parts and making a whole wizard feature, I'm going to talk about the whole series. Okay, the whole series is an assembly feature, special type of hole. It basically allows us to do like a match drill here at the assembly level. Granted, I could use the whole wizard as a match drill here at this level, but what this match drill does is it actually propagates back to the parts. So as I drop each one of these points on here, there it goes, I'm going to get 4 holes, and these 4 holes will go into each one of these 3 parts, resulting in 12 holes, or 3 different features that I was able to do all at once. Top hole is going to be a counter bore for number 8. Middle hole is going to be a clearance hole. The last hole is going to be a tap, and in 2007 we have the ability to specify the ending part. So I'll pick that. As I hit OK, I get my hole thrown in here. I'm going to go ahead and hide this sketch. Okay, so as I open this part, as I made mention, this whole series will propagate back to the part. So as I open the part, we can see that that is in fact happened. My counter bore for number 8, that was not there yet. If I take a look at my gasket, it has a number 8 clearance hole. And then my base here, I've got a number 8 tapped hole. So this whole series can really save time. However, when you're doing that, it is an external reference, much like the gasket was. So if the assembly changes, these parts are going to wind up changing with it. And this is a good thing if you know what you're doing. As they say with Spider-Man, my son loves Spider-Man. With great power comes great responsibility. That is true here with your external references. If you can maintain them, it's going to save you a lot of time. If you cannot maintain them, it's going to be a major headache. So keep that in mind when deciding whether or not to use them. Okay, the next example here we're going to show for mirroring. I just showed whole wizards, so I won't really cover that too much more on this part here. But as I take a look at how this part was made, basically up to here, we drew one tab and have one hole, and because the location of my planes was planned out in the middle here, I can now take advantage of these planes and mirror that tab over and then mirror it again, and then finish my part with some additional cuts and fillets. So the current theme here is the more you can plan out, the quicker changes will happen for you. Okay, now we'll go ahead and talk about the next file I have prepared for you. In this file here I have some linked values, I have some equations, and I have some file properties. And we'll also talk about design tables, all in short order. Now as I roll back to take a look at our first feature, first sketch, you'll see here I did another rectangle with a center line going corner to corner, utilizing that midpoint relationship with origin. And remember, the advantage to that is it places all the standard 3 planes running through my part, since origin is the intersection of those standard 3 planes. And just from a sketching standpoint, this gives us 3 additional places to sketch. What I'm talking about here is if this cube were drawn with the lower right hand corner at origin, 3 of those faces would occupy the same location as the standard 3 planes. So by having that origin in the middle, moving my planes to the middle of my cube, I now have a total of 9 different places to open a sketch, whereas on a standard cube, sketched out the way I previously mentioned with the lower right hand corner at origin, I'd only have 6 places to add a sketch, as like I said, 3 of those places would occupy the same spot as the other 3 planes. Now as we take a closer look at this sketch, view normal 2 on the front, normal 2 on the front, there we go. I have this rectangle has now been converted to a square because I've said that this edge is equal to that edge. So this is what we were talking about when I say the proper use of sketch relationships. I can specify that this edge is equal to that edge. However, you may run into a scenario where you want a dimension linked or equal to another dimension either inside the same sketch or maybe somewhere else in the model. Now in this scenario I could have added another dimension and linked it to this dimension here inside the same sketch, but since they were both line entities, I'd most likely want to use sketch relations for that up front. However, this does kind of show us how we can think about link values and equations. That is, the ability to add relationships between dimensions. Okay, so in this scenario here, this dimension is actually being linked to my cube depth. So as I double click here, I can see my 1 1/8 depth that was generated by my extrusion has now been linked to my sketch value. Now as I go ahead and populate the rest of my cube, we'll go ahead and take a look at the equations folder. As I hit the plus sign here, I can see my link value groups. The cube, which is 1 1/8, and a depth group that I was using for something else here. Now, if I take a look at my configurations, I've got this cube changing size. However, to accomplish this change, I was only changing one variable because of the way I set up my equations. And to kind of show that, I'll go ahead and change one of these to 3 inches. And as I change that to 3 inches, you can see that this thing changes proportionally. Okay, it's not like a standard scale wherein a standard scale looks like you're just zooming in. You can see that everything got larger proportionally. So I'll go ahead and change that dimension back to 0.75, and we'll take a closer look at those equations that I already put in here. Okay, so as I take a look at my equations folder, I can edit my equations, and from here I can see, I'll go ahead and hit the plus sign to kind of show each one of these sketches so we know what everything's talking about. Okay, here my large hole diameter, which is this sketch here, I wanted that to be equal to my cube square minus 200 thou. So cube is the name of the extrusion, square is my sketch, so it's basically taking that link value minus 200 thou. So as this thing grows, my circle will always maintain a 200 thou distance from this outside edge, this outside wall. Now the other equations that I've applied here is the middle hole, the cut, the middle hole here, that's equal to my larger hole divided by 2. So whatever this is, that must be half of it. Same thing with the smaller hole. The small hole is going to be half of the larger hole, and that's what I got going here. Okay, large hole divided by 2 is the middle hole. The small hole is the middle hole divided by 2. Now, to show a design table with all this mess, you'll notice that I have 3 configurations. Okay, so any part that you already happen to have configurations with, you can go ahead and insert a design table. So from the insert pull down, I can specify design table. Okay, and through an autocreate, because I already have configurations, it's going to go ahead and pull in the differences between each configuration. So as I hit OK, I made mention before, I was basically modifying one dimension to get these changes. And here it's showing that dimension that I was modifying, the 0.75, the 1.5, and the 1.125. Okay, so as I click out, you'll notice that my design table generated different configuration icons. These have now turned into Excel icons. So to make additional configurations utilizing a design table, I'll just go ahead and edit my table here. I can go ahead and copy what's already here since it is Excel, paste something in here, and now give it a new configuration name. I'll call that one 4 across the board, and I'll make these 3 since that was one of the dimensions that I just was demonstrating earlier. So as I click out, the design table will make a configuration for me, and now I can see that configuration like that. Now, if you can plan out your relationships of your features within your model, this should give you the ability to write efficient equations that can be utilized in a design table for configurations. In fact, anytime you have over 2 configurations, I recommend throwing in a design table because that will show you the changes between each configuration. After all, when you have just 3 configurations changing only 2 variables, you have a possibility of 9 different outcomes, so losing track of what's going on is not that hard. The next thing that I wanted to cover in this file was the file properties. So as I take a look at file properties here, under the custom tab, I have 3 different properties. I'm controlling description, and a custom part property, and a material. You'll notice that my material is actually linked to my tree. Okay, my material is here, 6061 alloy, and I was able to do that from the pull down here, material. Okay, and the whole idea why this is important for design planning is you're going to have variables that you may want to control. Things like part number, description, who drew this, material of course, all those other variables that you may want to put on a drawing or maybe even have show up in a bill of material. Okay, and basically I'm building this all up from the next file that I've got here. It's basically a drawing taking that cube in an assembly, and on this drawing we've got multiple notes that are pulling in properties from my part. So as I drop in a note here, I'll just kind of show you how this note thing works. Okay, I could go ahead and link right away to a property. And when I do that, I get this dialog box, and what this is basically asking me for is, okay, I can pull links from several different areas. Where would you like me to pull that variable from? Now, to kind of describe this dialog box, I'll do that here in a second, but just to basically show you, current document is the drawing itself, and from the pull down here, I get my custom drawing property. If I say model and view specified, that pulls up my assembly properties. And so to make sure that this goes smoothly, I'm going to go ahead and open the assembly, and we're going to take a look at its properties first. From the file pull down, I can specify properties. Yeah, file, properties. Okay, from here I have my description, custom assembly property, and custom assembly value is the value of my custom assembly property. I have the weight of my assembly all plugged in here. Okay, so far the part had its own properties, the assembly has its own properties, and finally the assembly is going to have its own, the drawing is going to have its own properties. So if we go to file properties here, here is the description for my drawing and my custom drawing property here. So I hit OK. I've got different notes linked to different areas. I took screenshots of the dialog boxes so I could kind of tie this in. Current document, as I said, is the drawing that we're looking at. So as I take a look up here, linked to custom drawing property, which is the custom drawing value. Okay, the reason I named this stuff this way was so it would convey where everything's coming from. Here I have text that's attached to the view below, and linked to the custom assembly property. Okay, anytime we drop a note, whatever view you're closest to, it tries to attach to. So that's what it's talking about there, being attached to that drawing view below. The third one, the one that we most frequently use, linked to custom assembly property number 2, and that's linked through model and view specified and sheet properties. Okay, this is referring to our sheet properties dialog box. At the bottom of that sheet properties dialog box, we have use custom property values from the model shown in which drawing view. The only reason that this is here is the fact that we could have a drawing that has an assembly view, a part view, maybe even a subassembly view. In other words, 3 different drawing views all containing different models or different top level files. And since we're pulling file properties, then we want to make sure that we're looking at the right top level. So for this demonstration here, model and view specified, it's currently pulling in this drawing view which contains the assembly, therefore I get the assembly values. Now the last one here is the component to which the annotation is attached. Okay, that gives me the ability to add a note with a leader, and whatever part this thing is touching, it's going to go ahead and access that file's properties, that part's properties. And so that's how come I can see that this is linked to the custom part properties. Now, all this stuff is great information, but it's also useful in our bill of material. Okay, from here I can see that I'm pulling in the part material. Okay, to basically add a column with a custom property, you basically wanted, select your whole column and then insert a column to the right or left. I'll go ahead and drop one in here, and now I could specify a custom property. Grab the whole column first, right? Custom property, and pull it from the part. So I can specify custom part property and hit OK. The advantage to doing it this way is if I go back to my part and I start making changes, maybe I change my material to, let's say, brass. Now when I go back to my drawing, that material has been updated. Likewise, I could do the same thing to the custom part value. So as I open this part here and take a look at its file properties, custom part property, custom value, I'll say updated. Hit OK. My drawing's going to update with that same value. So we take a look here. Custom part value updated. Okay, I know that was a lot, awful quick. I invite you guys to visit our webcast archives. If you're a subscription customer, just request a login and you'll be able to gain access to all of those. And you'll be able to watch this again. Okay, next we're going to go ahead and talk about best practices. Now, other people, coworkers, other vendors, whoever you send your models to, they're all going to have to deal with your models. And I say deal with because you know how it goes. It's the 11th hour, deadlines are right around the corner, and you don't have time to deal with having to fix a model that's blown up or isn't going to change easily. So the point to this webcast is basically show you how important it is to plan out your models so that everybody else that has to use them will know what's going on. Your models will change easily, therefore you want to keep everything simple. When I talked about complicated sketches, I also talked about avoiding complicated sketches because you might think it's funny that somebody else might not be able to figure out what you were doing in your sketch, but the proof is when you come back to that model 6 months later and you're the one that drew it and all of a sudden you can't figure out what's going on. Okay, then you'll have a chuckle with yourself. Okay, so you want to make it easy for everybody. The other things that I want to describe here is you want to clarify your design intent. And what I mean by that is you want to use construction geometry when necessary, especially if it'll make stuff make sense right away. You'll always want to use fully defined sketches. That's another topic that I covered through one of the webcasts, Interpreting SOLIDWORKS Feedback, available in the archives. From an assembly standpoint, you want to make sure that your components are fully defined in their positions in the assembly. This will help convey intent. You may also want to add comments or notes to features or add additional information to the design binder. This is also available in another webcast that I covered, Communication through SOLIDWORKS. This webcast, along with those other two, is pretty much the trilogy of keys to being a SOLIDWORKS certified professional, if you will. Granted, you still have to take the test, but if you get these concepts down, then you're going to have a much easier time passing this test. Not to mention, you'll be an elite user because you'll know how to figure out what SOLIDWORKS is telling you. You'll know how to make your models easy for everybody else to use, and now you'll know how to set up your models so they're easy for change. Let's see here. You also want to name sketches, dimensions, features, planes, mates, etc. As I was going through the equations, you'll notice that I had named some of those sketches, like large hole, middle hole, or medium hole, etc. Now, in addition to all this, you want to keep simplified sketches. I mentioned that. You want to avoid contour sketches. What that means is if I have a square and a circle inside that square, that's a multiple contour. You want to avoid stuff like that. If you have a part that would benefit from a contour sketch, then what you'd rather want to do is go ahead and use that as a layout sketch. Layout sketches are nice, and they do allow for great ease of changes. You want to convert that layout sketch into different sketches, and I'll go ahead and show a example of that. Another thing to keep in mind while all this other stuff is you want to avoid making unnecessary parent-child relationships. Okay, when you make parent-child relationships that you didn't intend for, when you delete a feature out, you're going to take out all of its children. Therefore, if you have a feature that doesn't necessarily need the other feature to exist, but through some accident, either intentional or not, you won't be able to get rid of that parent feature without taking out the child. So I'll show a couple examples of how to avoid that. Things like using the from option in extrude, or utilizing your standard 3 planes or datum planes for your sketching instead of sketching on a face. So as we take a look at SOLIDWORKS again, the next example here is number 15. Okay, in this scenario here we were talking about clarifying our design intent through using construction geometry. Now, through user enhancements, when I go to revolve this, you'll notice it picked up my center line. However, you can use other lines other than center lines. Okay, so in this scenario here, I can use any one of these to revolve this profile. Now, if you happen to have no center line whatsoever and this revolve feature blows up, then it might be difficult for somebody else to try to figure out what your intent was. So even though it's not required through what the software is capable of doing, it's still a really good idea to communicate your intent through utilizing center lines. This also bears out for making mirrors. So I take a look at my sketch mirror here. Okay, entities to mirror, I could say these here, mirror about. Okay, obviously we want to use a center line, but to show you that it'll mirror about anything, okay, it'll literally mirror about anything just like the revolve did. So you want to make sure you keep all that stuff clean. Use center lines whenever you can. Okay, the next example here is if you have a multiple contour sketch. Now, typically you'll be able to tell when you got a multiple contour sketch if you hit extrude and you get the selected contours dialog box open. Okay, unless you're intending to use multiple contours, this means that there's something wrong. the way that the multiple contours work is I could select different regions for my extrusion. Okay, and while that kind of looks neat, it's more of an advanced modeling technique and not something that should be employed every day. Okay, I can take any one of these and build a whole model from it. Now, what I would recommend doing instead of that would be to open a brand new sketch on the top plane here and go ahead and convert these other lines. So as I select this chain, I can go ahead and specify convert. That pulls out that one contour. Now I can go ahead and extrude that. You'll notice select the contours is not bugging me. Okay, and I can do the same thing over and over again. Click on the top plane, add in another extrusion, grab one of these lines here, and convert it, and go from there. Now, this gives me the same flexibility as I would have if I used selected contours, because if I edit my original sketch and I change the dimension, and when I exit out, that model is going to update because this line was converted from the original layout sketch. So use layouts, not contours. Layout sketch. Okay. Alright, the next example that I have lined up here for you, as we're running out of time here, is going to be an extrude from. Okay, in this scenario here, I was mentioning try to avoid making unnecessary parent-child relationships. Okay, what I mean by that is if I click on this grandchild bridge sketch, and the reason I'm calling it a grandchild is because it's relying on a bunch of different things. If I take a look at the parent-child here, I can see that its parents is a move copy body whose parent is the right sphere. Okay, that means if I wind up deleting this thing here, it's going to take that with it. But to kind of show that, I'll go ahead and extrude that and go up to here. Okay, now if I delete this, not only does it want to take out my extrusion, which I expected it to do, but it also wants to take out the sketch. Okay, so that's gone. Whereas in this scenario here, if I took my bridge profile and I did an extrusion here, rather than going from my sketch plane, which if I did it would cause this scenario here, it would block up this area, and that's not what I'm looking for. I can specify from a location. Okay, here I could specify from an offset, which would enable me to start my extrusion out here, even though my sketch is back here. Okay, and the whole point of doing this is that we could sketch under standard 3 planes or a source set of planes that are at the very beginning of our tree that will never be deleted or moved. And from there we can make our extrusions, our cuts, being able to delete anything in the tree and still preserve the sketch geometry. After all, sketching is as difficult as solid or skids. Therefore, if we can preserve those sketches, then we're going to have all that we need to make the changes no matter what happens. So one of the starting conditions rather I'm going to use is up to vertex, or from a vertex rather, and then from here I can go up to body on each one of these, up to body. Okay, and now that's being generated even though the sketch was way back here. And to kind of show that deleting this sphere is not trying to delete the sketch. I can do that here as well. I can delete that. Okay, and my sketch is still safe. Alright, one last example here. As I take a look at design intent, we were talking about the stacked. That is, I extruded this on top of here. Okay, the final drawing probably doesn't want to have that dimension on the drawing. Manufacturing approach says that if everything's done and extruded from the back plane or back face, then I'm going to get the same dimensions that I need to show up on my drawing. So even though this thing could be made in both scenarios, go ahead and start everything from most likely the top plane. Okay, remember, if this thing is started on the top plane I could literally delete this thing here and it won't take out my sketch. Okay? Whereas if this was reliant on the back surface, edit sketch plane, now when I try, aside from flipping my orientation, now it'll try to delete my sketch. Final thoughts. SOLIDWORKS productivity enhancements tend to automate manual processes and tend to focus on eliminating this dependency that I'm talking about. However, if your models are properly planned out, you can be more productive today. What that means is basically take your time, plan it out. Even though you take more time up front, it's actually going to be quicker in the long run because it's quicker when you only have to do it once. The Certified SOLIDWORKS Professional Exam tests your grasp of design intent. It's not about complex surfacing, whether you can model a loft and a sweep in some ergonomic surface. It's all wanting to test design intent, because this is what companies need in a SOLIDWORKS user. It's, can they build models? Okay. Can they build models that can be easily changed and accommodate the changes that we need? So for more information on the SOLIDWORKS Certified Professional, please visit solidworks.com. And finally, I want to thank you for joining us for another productivity webcast. I hope you found this information enjoyable and useful. Also, for additional tips and tricks, don't forget to check out DDI's podcasts. Those are available at ddicad.com, or go to the website podcast.ddicad.com. And as I made mention earlier, if you're a subscription customer, please sign up for a password at our customer center sign-in, and here's the link for it, ddicad.com, support sign up. And this is where you can gain 24/7 access to this webcast and others, as well as additional SOLIDWORKS goodies that we have packed away in there for you. If you have any questions on this topic or any other technical issues, please contact us here in tech support at 1-800-575-7543, or you can give us an email at support@ddicad.com. Until next time, I'm your host, Joseph Richter, and before you leave, if you wouldn't mind filling out the survey here that we're going to display next. That way you can tell us what you thought of it and any other topics that you might want to see us do in a webcast in future webcasts. The other thing I want to mention is that make sure you put in your email address. If you just fill out the survey and tell us a good idea, unless we know who you are, we won't be able to get back to you. We have a scenario where people will ask questions and not give us any way to get a hold of them. So please be sure to do that. Thank you and have a good day. Take care. Goodbye.